So I just want to talk a bit about the architecture of core logic. I have to say, it's been pretty sweet that Fogus put this together. I actually can't think of a better group of people to sort of kick it off. The talks that came before, I was afraid my talk would be too fast or cover too much, but everybody did a really great job of really, I think, setting the stage, and I'm really excited about Nada as well as Dan and Will's talk after this. So the architecture of core logic. I'm going to have to assume that you guys are familiar with mini-canron. I have too many things to say. So I'm assuming you've seen or will eventually see my Strange Loop 2012 unsession on how we interpret what I sort of refer to as vanilla mini-canron, which is actually not the mini-canron that's in the reason schemer. I actually based originally my version on the version in William Byrd's dissertation, which is really amazing. It's really amazing to get a dissertation and you get a working implementation. Everybody's dissertation should be like that. So I'm not going to talk about the sort of monadic stuff. This is like the last page in the reason schemer, which just doesn't make any sense. What's amazing is that eventually you understand it. It's actually what's incredible about this code is it's really a very tiny part of mini-canron. Unification and other features actually constitute a lot more code. The search is quite simple. And in fact, the Clojure source code is now actually, instead of being 200 lines of code, it's 4,500 lines of code. This is still the only part that has anything to do with search. So this is very simple, eventually, once you get it. But I'm not going to talk about this. Well, I do want to say that the only difference between the scheme and the Clojure is the Clojure stuff is built on top of protocols. And this is something I fell in love with. I think if you do Haskell, you sort of get some of this from type classes, and in Java, you sort of like the sort of Java libraries that really rely on interfaces. But the big idea behind protocols is that I really love this book, The Art of the Meta-Object Protocol. If you haven't read it, you really should. It's sort of been celebrated as like one of the greatest books on object-oriented programming, which I actually don't care about. I think what's important about this text is what Klaus let people do, is people said, well, objects are a good idea. And we have incompatible Lisp object systems. We want them to work, right? So the idea was distilling a set of protocols so that you could support incompatible object systems. And that's the big idea. That's really the big idea, and sort of at the essence of what I would like core logic to do, to allow many different sort of logic systems to interoperate. So I'm going to focus on constraint logic programming. Prolog is a constraint logic programming language, which fortunately somebody mentioned. This is a quote from The Art of Prolog, which first came out in 1986. And they say, an exciting development within logic programming has been the realization that unification is just one instance of constraint solving. And Ryan Sr. alluded to that in his talk. So if we're going to talk about our approach to constraint solving, we have to start with C-Canron. Claire Alvis, William Byrd, Dan Friedman, and others, they made this really great paper for the Scheme workshop. And I'm really excited. Many of these people are here. And so what they did was they said, we want to extend mini-canron to constraint logic programming over finite domains, as well as we want to prove that we can actually put disequality constraints on top of the same framework. And for me, this was the big idea, because I really love this idea of many different constraint solvers and logic programming systems interoperating, right? So this was the last paragraph is really important in this paper. They talk about this. So let's dig into some code. So I'm going to try to do things at a high level, and then maybe talk about some details about how we interpret C-Canron. So we have a substitutions, and it's been talked about, so I'm assuming you know what that means. We want to be able to map logic vars to their known values. But in the constraint logic system, we need to have the constraint store, right? We need some place to store constraints so that we can delay their running and then pull them out and then run them when we can. So the constraint store does something similar, but it maps logic vars to the sets of constraints that apply to them. And constraints are just functions. Then the substitution needs to do something new, right? It used to just store single values for variables. Now the substitution needs to be able to store possible ranges. And in fact, we need some way to efficiently refine information. Remember, this is quite different from what happens in Prolog. You unify, you say x is 1. Well, that's it. X always has to be 1. But it's very different in this system where we can say x is between 1 and 10. And then somebody says x is between 9 and 20. Well, then x has to be 9, right? We do some sort of intersection. So we need to be able to update information in a way we didn't have to do in the past. So CoreLogic, again, is quite large. So this is what's beautiful about Mini Cameron is Mini Cameron is simple. Well, again, once you get it, the substitution in Mini Cameron is just a list of pairs. But it's quite a bit more complicated in CoreLogic because we want to do more things, and we're very interested in making things faster. So in the substitution, if you read C. Cameron or if you read these other Mini Cameron papers, they often make the substitution bigger and bigger and bigger because they want more stuff. So our thing is particularly big because we want a lot of stuff. So here's the substitution map. We store the map, the bindings from logic vars to variables in a persistent hash map. And this has been great. Lindsay Cooper and Dan and Will, they wrote this really great paper about how they used better data structures to get better performance. And I was able to just swap in persistent hash maps, and we were able to achieve about the same performance results for the fastest version of Mini Cameron in that paper. So that's pretty neat. We have a field for tracking var changes after unification. So we run a bunch of unifications, then we know, well, we better make sure that no constraints have been violated. So we track that in a var. We also have tabling, right? So it used to be, I implemented Will's version of tabling, and some people who were doing static analysis of Java ran into lots of bugs with it because the tabling persisted between runs, and this is undesirable. So now the table is an atom, and it's resident to a single run, and that's quite nice. We're going to talk about the constraint store in a second. We also have a constraint queue. So I'm going to explain in a second, but we want to do things differently from the way that C. Cameron's scheme did them. So we actually keep a queue of constraints that we're about to attempt to satisfy. There's another performance optimization where we actually keep the constraint IDs that are in the queue in a set, so we never put redundant information into the queue. So again, you can sort of see we have lots of fields because we're trying to just reduce the cost of constraint solving. One little minor detail is that the occurs check flag is now inside the substitution because CoreLogic is lazy. It produces a lazy sequence of results, and dynamic binding and lazy sequences don't work well together. We used to set the occurs check with dynamic binding, and we got rid of that. OK, so the constraint store, the thing that stores constraints and maps vars to constraints. So again, we have this thing where we map a var to the set of constraint IDs that apply to it. We map the constraint ID to a constraint, and we do this with integers. I believe I tested at some point if I could just put functions directly in there, and for whatever reason, it was faster to sort of go from var to a set of integer IDs, and from integer IDs to the constraints. We keep a counter just so we have fresh IDs for constraints, and we need to track the running constraint to avoid infinite loops, and I'll explain that in detail. So the constraint store is just a thing. We need to be able to add constraints, remove constraints, update them, run them, query the constraint store for which set of constraints are applicable. And we have this kind of crazy thing, which I'll explain, because when you sort of pursue performance, often you have to do things a little bit differently than you would like. So I want to start with a motivating example about how we took C. Cameron and we sort of changed the way that it worked. And this starts with yet another logic puzzle. But hopefully here, the point of this logic puzzle is what CoreLogic is used for, but how I saw there was a problem with this particular puzzle and the behavior of the C. Cameron scheme version. So the implementation of this puzzle in the C. Cameron paper uses long addition to solve this problem efficiently. Most users are not going to want to formulate their problems in this way. So I tried to write in a much more natural style using C. Cameron's scheme and Petit Shea. And I ended up with something like this, right? So this is Ryan Sr.'s code sort of alluded to this. At the bottom, we have to create pointless intermediate values, right? And then we have to do the math, and we have to go back and declare all their domains. And then even worse, it takes 42 seconds to solve this in Petit Shea. And Petit Shea is one of the fastest schemes. This has nothing to do with the performance of Petit, right? And so I had to investigate what was going on. So I recalled there's a sort of section in the concepts, techniques, and models of computer programming, which has already been mentioned, which is very good. And they sort of show a couple things. Number one, they showed this puzzle, and it's very nice. The presentation is very clean. You have some variables, set the domains, set some disequalities, and boom, you just get to write the equation, right? That's kind of what you want to do as a programmer. You don't want to write things in strange ways. But the thing that really struck me was that they said, once the constraints are done, you can search the entire space of the solution in 6 steps. So why was it taking Petit Shea 42 seconds to solve a search space with only 6 possibilities? So I ended up debugging the C-Cameron scheme version. It turns out that C-Cameron only runs interval constraints once. And this is because they wanted to avoid an infinite loop. Right? You have a constraint, it triggers other constraints, and the thing is they wanted to take the original constraint out because the next constraint might trigger the original one, and then you would just get stuck. Right? And what happens is that they run all these interval constraints, but they all get lifted out of the store, and they all come back in at the end, but they all only get a chance to run one time. And then those logic vars that have 9,000 possible integers, you're going to enumerate all of them. So the 42 seconds was coming from the fact that the constraints don't get to run enough. So I had a talk with Dan. I had an idea. I was like, Dan, the C-Cameron thing, we're at Strange Loop 2012. I was like, Dan, the C-Cameron thing, it doesn't quite work the way that I want. And I sort of thought, what if we do things just slightly differently? When a constraint runs, it will trigger other constraints, but instead of running them, we queue them. Right? This is the big idea. We put them into a queue. And what happens is that once that original constraint is done, we now have a queue of constraints that need to run. And what will happen is we'll pop off the first thing in the queue, and it will re-queue the original, and that'll go back into the queue. And the fixed point is simply collapsing the queue up into the point that no constraint can actually change the domain of a variable. What will happen is a constraint will run, and no variables change values, and then that constraint won't re-enter the queue. So this is how we find the fixed point. So just to illustrate this again, we have some addition constraint. It triggers multiplication and another addition constraint to enter the queue. We're done. We move the multiple constraint and we get to run it. It puts the original addition constraint back in, and so on. So there's a snapshot of what the queue looks like at the largest size for solving send more money. So nearly every variable that's involved is in the queue at this point. And this is what you want to see. Right? They're just going to keep running until they find the fixed point. So some numbers. We end up having about 578 calls to run constraint, and we see about 22 calls to map sum. So this is this is better, right? Map sum is the search step. So there are 22 calls, so we're getting closer to 6, but we're not quite there. Still, this model is great because, let me just skip, oops. Well, I'll show it in a second. So the other thing I changed was I wanted the syntax to look like Mozart does. I didn't like to do all this manual stuff. So this, you can actually write this way. Ryan Senior sort of showed a simplified thing. Equations can be written in a very natural way. There's this thing called FDEQ. It's a macro that walks all your arithmetic expressions, adds the intermediate variables, and then we do domain inference. So you don't have to talk about intermediate values at all. So you can write inequalities and equations, and it just works, which is, I think, pretty cool. And it's competitive in terms of expressivity with the Mozart OS. And it's very fast, 15 milliseconds. Right? OK. So again, it still involves too much search. For example, when Ryan showed his thing, I actually think the 25 seconds to solve that equation was quite long. And that's because there's more work that we could do. You can actually set up a new kind of constraint that actually tries to simplify two sides of an equation. Like if you have an equality, you can actually do more simplifications than what addition and subtraction do. So you can add more intelligence. So again, we don't have equation level constraints, and that could sort of get us closer to what Mozart OS is capable of doing. So I just want to break down constraints, sort of remove some of the mystery. So like goals, constraints are just closures. They're slightly different in that instead of returning a function, we return a reified object. So functions are not primitive in Clojure, and this is actually quite nice. We can basically make constraints act like functions and yet provide the metadata that we need for this to work. And this is cool because we don't need to do this via macros. We can actually do this in an explicit way. And later, if we need macros to sort of clean up the syntax, we can do that. So this is, for example, the constraint for making sure that some variable has a particular domain. This is the body. You can invoke it just like a function. It's just like a function. It takes the substitution the same way that goals take the substitution. You do some work. But then the meta stuff is provided via protocols, right? We can ask the constraint, what were your parameters, right? And this is simply implemented as a protocol implementation. We can ask the constraint, which changes do you care about? Do you care about changes in domains, or do you care about changes to the substitution map, like when some var takes a concrete value? And this is quite nice. So there's protocols for all this stuff, and many different constraints need to do many different things. So that's nice. We see that we have some language for describing the world of constraints we might want to implement. So just a sort of a technical thing. that I thought was interesting was when I was getting through C Cameron, it was hard for me to see what's the role of a constraint? What's the sort of life cycle of a constraint? Like, how does it interact? Because when you run a constraint, some stuff happens, but then it goes into the store, and then some different stuff happens. So it turns out that currently what we do is all constraints are wrapped in this thing called C-goal that sort of figures out what needs to happen. First thing you care about, can you run the constraint? Are the parameters either sufficiently instantiated, or do they have domains such that the constraint can do some work? We run it. If we fail, we return nil. If we get a substitution, we can do more work. And then immediately we check, is the constraint entailed? Can we just discard it? Did it run once, and are we done? And this is kind of nice, because this avoids any overhead. If a constraint runs and it's done, boom, we're done. It's gone. It never enters the store. We don't have to deal with it, so on. Otherwise, it goes to the constraint store, and then we do things actually a little bit differently. Because once it's in the store, the likelihood is that the queue is filled, right? The queue is filled, right? There are things in the queue ahead of the constraint. So the first thing you want to do when a constraint runs is say, perhaps you're already entailed because some other constraint ran before you did. So these tests are now sort of done in a different order. Then once we say, were you already entailed by other constraints? Then we say, OK, you weren't. We run you. Then we do the tricky thing that helps the fixed point. We set the constraint as, we set a sort of flag on the constraint saying it's running, and then we say it's done. OK, so I want to point out some complications. So when you try to optimize things, you often run into trouble. So we have LVARs. And so the first thing that I encountered when I read Dan and Will and Claire's paper was, where are we going to put domain information? So they ended up putting domain information into the constraint store, and I didn't really want to do that. Originally, I was like, I'm going to be clever. I'm going to stick them directly into substitution. This actually caused a lot of trouble because suddenly domains, you really don't want domains to be directly involved in unification, and putting them directly into the substitution map caused issues. So I didn't like that. So we have a solution. There might be better solutions. In fact, part of this talk is just to get people to understand how it works, and maybe you'll say, I don't like that. I think you should do it this way, and we're totally open to that. So we have this new thing, which is sort of like a container. Normally, LVARs just point to closure values, just raw closure values. But now, because we want some place to put domain information, a logic var can be unbound, yet have domain information. And so we wrap it in this sort of wrapper type. And then the thing is, we don't want to break any contracts about the way that sort of primitive mini-Cameron stuff works. So walk, which is the primitive lookup, like what value is associated with a var, we changed walk to know about subst value such that no user of walk will ever have to deal with this, right? And that's kind of what you want. Though constraint solvers do have to know about it a little bit, but we've added helpers. So again, we would like to hide these details as much as possible because we might change our minds about how this works. So I just want to show walk because this sort of alludes to Nada's talk about nominal logic programming, which is a really cool way to sort of play around with theoretical computer science. But walk looks different. We don't talk about LVARs anymore. So when Nada did her work on alpha, sort of basically bringing alpha Cameron into core logic, we realized that, well, there might be lots of things people want to bind, right? Maybe you want to bind logic vars. Maybe you want to bind noms, which is what nominal logic programming is about. So again, every time we add a constraint domain, we sort of, our protocols get richer, and our idea of what somebody might want to do, what type of logic programming system somebody might want to write, sort of opens up. And then here's our little trick. We check, well, was the logic var bound to this thing that's holding domain information? If it is, sort of return the variable. Don't return this weird value that we use to store domain information. So another tricky thing that we ran into is var aliasing. So the constraint store, right? The constraint store is this nice thing, right? It's a way for us to quickly look up constraints on a logic var. And it's an optimization. We don't have to do any scanning. But once you decide to do that optimization, you have to be very careful about what are called roots, right? A logic var can point to a logic var can point to a logic var. If the user adds a constraint to y and y points to x, you better constrain x, because the constraint store only holds roots, right? So aliasing becomes a problem. And it was funny because I ran into many bugs, and then I started looking at the literature, and they said, yeah, if you're going to do a constraint logic programming system that has Prolog-like semantics, like Mozart Oz, yes, you'll encounter issues with aliasing. And then unification makes this even trickier because you'll have two logic vars which don't have concrete values, which both have domains. The user unifies them together. Then you need to do some switcheroos. Specifically, you need to repoint, merge the domain information, and if there are constraints, you need to migrate them. So way back earlier when I was talking about migrate, that's what the constraint store knows how to do. It knows when you point two vars together that you need to do some extra work. So just to demonstrate that idea, here's what the substitution map sort of looks like. It's grayed out because there's no real value for these logic vars, but they have domain information. So when the user unifies y to x, we repoint, and notice the domains got merged. So those domains got merged, and then we also additionally migrate constraints that were on y to x. OK, so that's probably a lot of stuff. But hopefully that gives you some ideas about how I like to take the stuff that Dan and Will and their students work on and sort of try to bring them into the Clojure context, try to make it a little bit more generic, and try to figure out clever ways to make it faster. So the takeaway here is I'm kind of into this idea of the art of the meta constraint logic protocol, right? So we want good protocols. I'll be honest, we're not there yet. There are many protocols that are not done, and they need a lot of work, and we're working on it. And of course, we'd love to hear about ideas and contributions. And that one of the things that I really love about art of the meta object protocol was they thought about, not only did they think about generality, they thought about the generality so much that if somebody wanted to write an optimized class, the facilities were available in the protocols themselves to very aggressive optimization. And we would like to do the same thing for logic programming. So it's often a question of, are we exposing the right things? Are we exposing enough? So again, I just want to say I'm excited about the talk about Alpha Cameron because this is a new constraint domain. We have to make some very interesting changes. With each new constraint domain, our confidence that we have the right set of protocols sort of increases. So I'm very much excited about the future. So future directions, things that I would like to see. I will say if you do any core logic, like I'm always amazed that people put this stuff into production, because it's very schemy, and that's okay, but it's very list oriented. And I think a lot of people are kind of like, what's going on here? I can't use hash maps, really. I can't use sets. And it's very strange. And so part of our goal is to really make logic programming more natural for Clojure programmers. You really should be able to use any data structure inside of a relational program, and it should work reasonably well. Also, something I don't like is that right now constraints and goals are not very polymorphic. This is another thing that's sort of, I think, off-putting for and sort of unnatural for Clojure programmers. We would like to fix that. There's some neat stuff that depends on whether people are interested in this. Probabilistic logic programming could be very cool. Will likes to talk about XSB Prolog a lot. If you're into Prolog, XSB Prolog has been able to do really cool things. I think tabling could be made a lot better in core logic. And then there's a question of, like, I hope you sort of try to play with the finite domain stuff because I think it's great. I think it's really practical. Hopefully everybody in the Clojure community just knows about finite domains. And then you'll start looking at much more sort of production solvers. Like core logic is sort of aimed at generality, and maybe one day will be really fast. We're working towards that. But once you sort of understand how the constraint logic stuff works, there are amazing tools out there, extremely fast constraint solvers. If you know how to use core logic, you can literally plug something like Jacob, or if you're doing other things, G-code. I hope I said those correctly. Anyways, so who knows? Who knows where we're going next? But hopefully you guys learned some cool stuff today.